All right. Yesterday we were talking about the parameters of operational amplifier, and we have seen quite a couple of parameters. But there was a question, maybe a request from some of you that they didn't understand this transient response. Is that right?
Yes, sir.
Okay. So we'll start with that. Okay. So let me do away with this. I'll start a new page so that it will be easier for you to understand. So we were talking about the transient response. Now, what exactly is a transient response? Basically, what do you mean by a response in the first place? Whenever you have a circuit like this and you apply a stimuli, okay? So this is your input, this is your output. We'll concentrate only on the voltage stimuli, okay? So how does the output look like, or how does the circuit respond to the stimuli is what is known as the response of the system or the circuit. Okay, up to this point?
Yes, sir.
Okay. Now say for example my stimuli, I apply a step input like this. Okay. So this black trace is the step input. How will the circuit respond? Okay. To this particular step input. There are various, depending on the nature of the circuit, it will respond differently. But for example, let us say we are talking about a simple amplifier. Okay. Now in that case, if I say we have a unity gain amplifier, simply means that output is going to be equal to input. In this situation, how does the amplifier respond is what is known as the response of the circuit. Now this is time. This is, let us say, voltage. So the response that we get generally is categorized into three different types. One is when the response is like this. Okay. Another one when the response is like this. Okay. And there is a third type of response which is just like this. Okay. So normally we call this as the system, we call this as the underdamped. This is called as the overdamped. And this is called as the critical. Okay. So this is called as the response of any system. Now have you understood? Okay, guys? Guys, are you there with me?
Sir, you were not audible for few seconds.
Okay, my question was, have you really understood now that various types of responses that the circuit can offer?
Yes, sir.
Underdamped, the overdamped, and the critically damped. ठीक है? This will learn in the control systems. ठीक है? If you have started that, I don't know whether you have started that or not. Have you started control systems?
Yes, sir.
Yes.
So then you should be in a position to understand these things. Anyways, so whenever any system exhibits such a kind of behavior, we call it as a response, obviously. Okay, it responds to a particular stimuli. Now, this response is again divided into two parts. Okay, this part is called as the transient response, and this part is called as the steady state response. Now, as the name suggests, steady state is when the output has reached a stable value. Okay, during this time, however, it will look different. Okay, and this part is called as an overshoot. This part is called as undershoot. Now, many times there is a compromise. If I want to make the system very fast, I have to make it underdamped. Okay, otherwise the response will be slow, as seen from the previous figure where I was showing the underdamped systems, overdamped systems. Okay, critical damp is very difficult to obtain. So most of the times the circuits will respond with an underdamped response like this. So this is the transient response. So given a particular stimuli to the input of an operational amplifier, how does it respond? So I said, that is the reason why I said there are two parts of that response. One is called as the transient response, and the other is called as a steady state response. Okay. Now this particular response, again, transient response, is characterized by various different parameters. What are those parameters? If we look at this carefully, okay, I'll use the same figure. I'll remove some parts over there, some things which are not required, so that it will not clutter the figure. Now look at this carefully. How there is something called as the parameters which we see as far as the transient response are concerned are what is called as the rise time, okay, and the percentage overshoot. Okay, so what is a rise time? Rise time is when I measure, let us say, 10% of this value to 90% of this value. So whatever is the time taken, call this as T1, call this as T2. This T2 minus T1 is called as the rise time. It simply means that it is the time taken by the output to go from 10% of the value to 90% of the value. Okay, and this actually defines how fast your device is. Okay, is that clear?
Yes, sir.
Okay, and then percentage overshoot. So percentage overshoot is what? This is the maximum amount by which the output will deviate from the steady state value. So this is your overshoot, and it is expressed in percentage. That's all. And I said that for LM, typical values for LM741C, the manufacturer says that at input of 220 millivolts, that is DC. We are having a step value, input. The rise time TR is 0.3 microseconds, and the percentage overshoot is 5. Okay, that is 5% overshoot. Okay, so this describes the response of the operational amplifier. Is this clear to all of you now?
Yes, sir.
Shall we proceed with the next parameter?
Yes, sir.
Okay. All right. The next parameter is again a very, very important thing, which is called as the slew rate. I have already defined slew rate, so we need not elaborate that. But just remember, what is a slew rate? What is slew rate equation? Yes, delta VO by delta T. Isn't that? How fast the output changes, okay, with respect to time. And we already know that the units are volts per microseconds. Okay. So for 741, slew rate is specified in the data sheet as 0.5 volts per microseconds. Don't forget this microsecond parameter. It is very important. Well, this is a general purpose operational amplifier, and so this is not a very good value, but we do have very good slew rate operational amplifiers. Examples of such amplifiers are LF351, and they have slew rate as much as 13 volts per microsecond. So these are very fast operational amplifiers. Okay, and very high speed operational amplifiers can even have slew rates as high as 70 volts per microsecond. These are very special devices and costly too. Okay, is that fine?
Yes, sir.
Okay, the next
Yes,
is
sir.
the gain bandwidth product. Okay, it is termed as GBP. Okay, now we know one thing: for systems, for amplifiers, we have one very important relation, that always the gain into bandwidth is equal to, yes, anyone? We have already discussed this. Gain into bandwidth is equal to, anyone? Is always constant. So if you increase the gain, your bandwidth will reduce. If you decrease the gain, your bandwidth will increase. Okay. So for operational amplifier, most of the time it is specified at a unity gain. So at gain equal to 1, the gain bandwidth product is specified. For 741, this gain bandwidth product happens to be 1 megahertz. What does this mean? In real sense, what does it mean? We are going to see this in more details, but for the time being, let us have look at the frequency, the response of the frequency response of the operational amplifier. That way, okay. Of course, we are talking about the generic response. So when you plot frequency response, how do you do it? You will be having the gain, and you will be having the frequency on the x-axis, gain on the y-axis. Now for the operational amplifier, you see the gain happens to be something like this. This is the frequency response. Okay, you'll see that it is the bandwidth is very less. This is for open loop. Okay. This gain is very high, but the bandwidth is very less. Here you can see here. But gain bandwidth product is a parameter which is specified at a gain equal to 1. Okay, unity gain. So I'll be having something like this. So let us say this is wrong. Okay, so if I mark this as gain equal to 1, whatever is the bandwidth, this is 1 megahertz for the operational amplifier. And as you can see, if the gain is less, for example, if the gain is somewhere here, the frequency response will be, the bandwidth will be much better. Like this. So if I increase the gain, the bandwidth reduces. If I decrease the gain, the bandwidth increases, which conforms to our concept that gain into bandwidth is equal to 1. Have you understood this? Guys, have you understood this?
Yes, sir.
Yes, sir.
Okay. So the next part is the next parameter is the average temperature coefficient of input offset voltage and current. This is again a very important parameter. Now these parameters are also referred to as average input offset voltage or current drift. Okay. Now this average temperature coefficient of the input offset voltage, what is it? Specified as, it is the average rate of change in input voltage. So it is, I can say, input offset voltage temperature coefficient is what? Is the average rate of change in input offset voltage per unit change in temperature. It is expressed in microvolts per degree Celsius. Remember this. So how much the input offset voltage changes if the change in temperature is there. Similarly, average temperature coefficient of input offset voltage will be the rate of change in the input offset current per unit change in temperature, and that will be given as in picoampere per degree Celsius. So just you have to replace this word average rate of change in input offset current per unit change in temperature. That's all. Now generally these parameters are specified for what are called as instrumentation amplifier or precision amplifiers only. You will not find that for general purpose amplifiers. Okay. Now there is a precision amplifier called as LM714, and the average temperature coefficient, that is delta VIO by delta T, is 0.5 microvolt per degree Celsius typically. Okay. And the average temperature coefficient of input offset current, that is delta IIO by delta T, happens to be 12 picoampere per degree Celsius. So these are all things which are specified for precision operational amplifiers. Okay, guys, are you able to understand one important thing? Do you see anything very surprising here? Guys, the people who have designed and analyzed this circuit can measure the voltages, and the voltage is fine. Current down to picoampere level. Look at the kind of instrumentation, electronic instruments that they have, okay, or that they have used or developed, so as to measure even 12 picoampere. Picoampere means what? What is a picoampere?
10 to the power minus 12.
Yes, this is a very small quantity. So just imagine how they must have measured it. Another important parameter is the long-term input offset voltage and current stability. So again, this is delta VIO by delta T. What is this T? T is time here. Okay. So it is average rate of change in input offset voltage per unit time, and generally it is expressed in microvolts per week. Similarly, we have delta IIO by delta T, which is expressed in picoampere per week. Again, these are specified for precision op amps. So for LM714, delta VIO by delta T happens to be 0.1 microvolt per week typically, and delta IIO by delta T, they say, is negligible. So it cannot even be measured. Okay. So this is called as a stability, temperature stability. The next is equivalent input noise voltage and current. Now we know that electrical noise is random in nature, and mostly it is expressed in RMS terms. RMS means what? Root mean square value. Okay. Now, generally, noise has got, you cannot identify the noise as far as a signal as at a particular frequency. Okay, because since noise is random, you cannot have a single frequency component there. So you have a range of frequencies over which that noise is generated. Okay, and so the noise voltage equivalent is normally expressed in terms of voltage square per hertz. Okay, so this is what is the unit for noise voltage, and similarly for current we have ampere square per hertz. Okay, this is just for your information. Now let us quickly summarize the important performance curves. So the typical performance curves. In a data sheet, we normally have these curves in data sheets. Which are graphs of electrical parameters affected mainly by three factors. So you'll have the three factors affecting the electrical parameters. One, change in supply voltage. Change in temperature. So these three factors, based on these three factors, you'll get different curves with respect to electrical parameters with respect to these three factors. Okay. We are going to have an assignment based on this to study the data sheet of operational amplifier. Okay. Now quickly we are going to have the summary of parameter evaluation for AC and DC applications. So which parameters are relevant for AC, which parameters are relevant for DC. So we make a table like this. So parameters or parameter evaluation for AC and DC applications. So whenever you are having DC application, which parameters you have to consult? If you are having AC parameters, which parameters you have to consult? This particular table gives you. This is for AC, this is for DC. For AC, you have the first parameter as input resistance. Similarly, for AC, DC also, this is important. Output resistance. Here also we have output resistance. We have the large signal voltage gain. Here also we have the same thing, large signal voltage gain. Output voltage swing. We've already discussed these parameters. Here also output voltage swing. Average input offset voltage and current drift. Here we have input offset voltage and input offset current. Long term input offset voltage stability. Here we have average input offset voltage and current drift. Now you'll be surprised. I mean, you'll be asking me, say they look same, very same, but wait, here is where the things will differ. Important here is gain bandwidth product. Here it is not. Here we have the long-term input offset voltage stability. These parameters, many of them are common, no doubt about that. Here you have the transient response. Next you have the slew rate and the equivalent input noise voltage and current. So just have a look at these parameters which are relevant for AC and which are relevant for DC. Okay? Guys, is that okay? Hello? Are you all there with me? Guys, please respond.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So these are the parameters of relevance to AC and DC. Next is another important factor which we call as the frequency response, which we have shortly seen, but let us see in more details. Now this is going to be the open loop response, frequency response. Okay, let me import a figure. So this is how the frequency response, open loop frequency response of an operational amplifier looks like. Do you see this? Guys?
Yes, sir.
So what does it say? It says that we have different frequencies. This is 0 dB per decade. There is no slope here. Here you may have minus 20 dB per decade, and so on and so forth. Here slightly you have minus 40 dB per decade, and then you have the 60 dB per decade. Okay, and these actually are different frequencies. So this is called as F1. This is roughly here we have F2, and then here we have F3. Okay, and if you look at the frequency response, it is accompanied always by the phase response, phase change. Okay, so here also we have a similar kind of behavior. All right. Now, interesting thing about any system, again, you learn that in control systems, that this change in these frequencies, I mean, the change in the response at particular frequencies, they have a certain first of all, there is one very important thing about stability. When do we have unstable operation? There is something called as Barkhausen criteria. What is this Barkhausen criteria? Do you know that? Guys?
No, sir.
No. I think in AEC you must have done that, or maybe in somewhere for oscillators. Have you done discrete oscillators? Phase shift oscillator, Colpitt's oscillator. Oscillators have you done or not?
No, sir.
No? Okay. Do you remember that transfer function equation that we had derived? What was it? What was that transfer function equation? With feedback? Do you remember that? Guys, we have not started studying yet, I guess. Which is very dangerous situation here. Hmm? Let me remind you of that formula. The specific formula which I have discussed earlier. There are various forms. I'm trying to find out which one I have shown you. Okay. Just hold on for a second. Okay, it was something like A divided by 1 minus A beta. Was it this? Yes? Guys, the very first few lectures. Let me see where we have done that. This shows differential amplifier. Should be in the first few lectures, I guess. Concept of system. I think we have done that somewhere. I don't remember where. But anyways, we have this as the transfer function. Do you remember this? We have done this, and we have said that since A is very large, my transfer function is going to be what? One by beta. This we have seen no earlier.
Yes,
Guys,
sir.
do you remember that? Okay, so look at this equation, and we have said this about the negative feedback. But when we have a certain possibility where this A into beta is greater than 1, when A into beta becomes greater than 1, this is one criterion, and the other criterion is that at the same time, the phase shift is either 0 degrees or 360 degrees or a multiple of that. In these two situations, we get what is called as oscillations. Are you able to understand this? See, again, I say there are three types of responses from the point of view of stability. One is something like this. Okay. One is sustained oscillations like this, if you excite the network. And there is another type of response where it goes on increasing. Okay. This is called as unstable output. So this is a stable system. This is critically stable, and this is an unstable system. So if I excite the system with a simple stimulus, this is how a stable system will perform, and this is how an unstable system will perform. So if you don't want instability for the operational amplifier, what is the care that you have to take? That is what is important here. So if you look at the open loop frequency response, it has got several poles. I hope you have studied poles and zeros. Yes. Hello guys, are you there with me?
Yes, sir.
Okay, I think there was a call drop. Okay,
Yes.
let us make it simple. Do you know the concept of poles and zeros? Have you
Yes,
studied the
sir.
concept of poles and zeros? So in simple plain words, our operational amplifier has transfer function with several poles and with zeros at much higher frequencies than the poles. So the poles are important here because most of the times at the pole frequencies you may have this kind of unstable operation. Okay. Now the poles can be found out experimentally, and as I said, using the Bode plot you can find out the poles, and these are the actually the pole frequencies. Pole frequencies are where the frequency response changes. Okay, so F1, F2, F3 are the pole frequencies. Okay. So here in this case we see that the transfer function has got 3 poles. Okay. And you will immediately see that at the pole frequencies, the phase response also changes. Obviously, that is the reason why you call it as a pole frequency, right? Now, it is quite important that whenever there is such a kind of change, whenever there is such a kind of change, and if by that at that particular frequency, if this Barkhausen criteria is satisfied, your system will become unstable. Your operational amplifier will become unstable. Okay, and so it is required for us to have some kind of compensation called as frequency compensation. So frequency compensation. For this circuit, we must have frequency compensation. How can we achieve that? We can achieve that by adding poles and zeros to the frequency response. Okay. Adding poles or zeros means what? We are actually changing the phase shift. We are compensating the phase shift so that it will not satisfy this criteria. Okay. All right. So there are 3 methods of compensation. One is the dominant pole compensation. Okay. Now, if you look at the frequency response again, this was with, let us say, no frequency, no compensation. What we do is we add, let me make it a little bit more. Okay. Like this. So there was no compensation. This is just a partial transfer frequency response of the operational amplifier. And what we do is using different capacitors, we add some certain poles. Okay. So what we do is either we add a pole and get a frequency response which is much lower like this. Okay. So this one is at, say, let us say C1. This is at C2. By changing the values of the capacitors, I can add these poles and compensate for the frequency. In a circuit, normally we have for operational amplifier, we do it like this. So there are certain terminals available. Let us say pin number 9 and 10 here in this case, and we add a capacitor here. This is that capacitor which I am talking about. Okay, these are your inputs, whatever. Obviously, it will be having some function. So I'm just drawing a circuit of an inverting amplifier like this. We are going to see more details about these things. But this is, so normally manufacturers, they give 2 pins they give for frequency compensation. Now this is an IC which is MC1530. It has got this way of compensation. The manufacturer provides this way of frequency compensation. Frequency compensation means nothing but addition of poles and zeros so that this particular Barkhausen criteria is not satisfied and the system does not go into oscillations. Okay. There is another method, another technique. It is called as the pole zero compensation. Okay. So there may be another way of doing it, like this. So again, some operational amplifiers will give you a certain terminal for compensation, and here you can add an RC. So this is CC, this is RC. This is called as a compensating network. So what this does is it introduces both a pole and a zero. Okay, and this can compensate for the frequency. If you look at the frequency response, so this was the uncompensated one, and by addition of this CC and RC, what we are doing is we are actually making the response like this. Okay, so this is after compensation. So what we are necessarily doing is we are modifying the frequency response of the operational amplifier with the help of external components. Okay, there is a third method called as lead compensation. So normally what is done, if there are no if the operational amplifier and the manufacturer does not give any facility for frequency compensation, what we do is in the feedback loop we connect the capacitor like this. We connect the capacitor in the feedback loop. This is one more method of compensation. Okay, so this capacitor will be doing that. What it does, so actually capacitor will add a positive, let us say a positive phase shift, which means lead. Okay, so actually it will change the phase response. It will change the phase response. That is called as the lead compensation. Okay. All right, guys. Hello, guys. Guys, are you there with me? Hello.
Yes, sir.
Yes, sir.
Hello, guys.
Yes, sir.
So have you understood this three types of frequency compensation? Basically, why do we require frequency compensation? To avoid the instability. And how it is done? It is done either by adding poles, or it is done by using adding poles or zeros, or by adding an additional phase shift, a positive phase shift using this capacitor. That is called as a lead compensation. Okay? You should know these things, because many times the operational amplifiers are not internally frequency compensated. You have to do that externally. Okay. This will avoid the instability of the operational amplifier circuit. Is that clear to you? Guys? Hello?
Yes, sir.
If you still have any doubts, you can just WhatsApp me or call me up even and get your doubts cleared. All right? Okay, with that,
Yes, sir.
we completely finished
Yes,
with
sir.
the first unit now, officially. All right, all the things which I wanted to cover. There were many things which were not in the syllabus, but then the way in which I wanted to complete this unit so that it forms a foundation, a strong foundation for the next units. Okay? So what I want all of you to do is go through all the lectures. My lectures, all the lectures are available on YouTube. Do you know that, guys?
Yes, sir.
Yes, sir.
I hope they are accessible to you.
Yes, sir.
Yes, sir.
Okay. So please go through the lectures so that if you have missed any point here, you can always cover it up. Okay? So I'll stop here for today.